Students, we are going to start the lecture number 15 today. So, as you know, in the last 5-6 lectures, I have been discussing about different machine learning methodologies, or rather how to understand the models for the machine learning. So, we discussed different kinds of models, like we first discussed about linear models, where we discussed about mostly regression and descent tree. Then we also discussed about linear SVM. I have discussed in the last lecture, started discussing about the neural network. We are going to continue on the discussion. At the end of this lecture, we will start discussing about clustering. So, let us see what we have done in the last lecture. That is very vital. So, we started with support vector machine. I described you the problem. Problem is very simple. Suppose we have data which is represented by closed circles and open circles. Closed circles means the black dots, each of these dots correspond to plus, and open circles corresponds to minus. How do you classify this data? Correct? So, can I use linear classifier? Answer is no, I told you, right. I can draw different kinds of lines to separate these two categories of points. I can draw this line, I can draw this line, I can draw different sets of lines. So, there is no unique solution exists for such a kind of classification problem. Instead, we can draw a street, I told you, right. The street can be drawn in such a way, the points which are lying on the gutters of the street are basically the ones which are called support vectors. Street will also have a central line. So, any data points which are falling below the data central line is called positive, or sorry, here negative, and above the central line is called a positive, right. So, basically this street defines a margin of a linear classifier, and important aspect for us to optimize is the width of this street, or rather margin of the street. So that it can be as big as possible, then we do not have the problem of misclassification. I discussed with you a lot, and that is what is the main theme or aspects of the support vector machine, which talks about maximum margin principle. And it is good in terms of, it is a very safe method. It allows you to classify points in a safe manner. And in this classifier, important aspect are these points which are called the support vector points. These data points are ones that margin will push up against. That means, we should draw the margins of this boundary or the boundaries of these roads on both sides, what we call in general gutters of the road, are by joining the points which are falling on these margins. Okay. That is what is the idea. This is the simplest kind of SVM, what is called as a linear SVM. Why this is very good method? Because if we make a small error in terms of location of the boundary, okay, that gives us least chance of causing misclassification or problems of classification, right. Remember, this actually works very well, and this was developed by Vladimir Papnik. He is a mathematician from Russia. He talked about this technique, and then he developed this technique. Okay. So, that is what the things which we discussed in the last lecture, but we also discussed a bit of neural network and artificial neural network. Okay. So, as you know, neural network is basically a machine learning algorithm which is typically inspired by the biological neural network, okay, biological neurons. And biological neurons have 4 different parts. One is called dendrite, which captures the input or the signals. Then you have a cell body which processes these signals, right. Finally, the processed signals is transferred by synaptic naps, or what is known as a synaptic links, and taken forward by the actions. and these neurons are interconnected. That means, there are millions of neurons in our brain which are interconnected, and that is why this forms a parallel processing unit. Each of these neurons process the data obtained from the dendrites and transfer this processed data to the next neuron. Again, next neuron process the data and transfer it to the next neuron by axon. So, therefore, axon looks like an output, right. Dendrite is kind of doing a job of input, and cell body is used as a processing of data. If this is the model which is used in biological systems, can we use this model for our own purpose? Okay. That is the answer. So, therefore, it tries to find mathematical way of representation of this information processing systems, and that is what we are going to discuss in the class today in detailed manner. So, neurons are connected, as I told you, there are 10,000 synapses. It receives some signals from the using these dendrites, which are then combined. Dendrites, you have seen that there are many dendrites, then these informations are then combined and processed by this cell nucleus. So, once input exceeds certain level, neurons can discharge, and this discharge can act like a spike which can travel through the body. Axon endings almost touch the dendrites, that is why it can transfer the output from one neuron to the next neuron, and transmission is always affected by neurotransmitters. Okay. They are nothing but a chemical substances which are released. So, now let us put together this information which you just learned in terms of a neural network or artificial neural network. So, what you can do? We can consider these inputs which are coming from data, basically nothing but data. So, they are actually acting as a dendrites, and then so dendrites, right, they are the dendrites which collects the informations from the data, and then we use certain weights to multiply these inputs. These weights can vary depending on the importance of particular feature or depending on how we think about the physics of the problem. So, once we multiply these inputs with weights, we can actually have summation of that for each of these. You can see just sum it over, and on the summation we apply certain activation function which we will discuss today in detailed manner. So, this activation function, one is sigmoid function as I discussed with you, 1 plus x 1 divided by 1 plus exponential minus z. So, this activation function then provides an output. Am I clear? This output again then fit to the next neuron. Okay. So, just like a biological neural system, so when you have various neuron exists, we can create layers here, and that is why some of these are called multi-layered or multiple layer structures, what is known as a MLP. We will talk about that, multi-layer perceptrons. Okay. So, hence this is the basic thing of neural network which you must understand, because neural network will be used for various kinds of things, not only for machine learning, also for deep learning methods. So, again let me explain to you, my inputs can be represented by x1, x0, x1 like xn, which are nothing but which are data basically, and then we multiply each of these inputs with a weight factor. Okay. And I told you why we multiply that, because each of these inputs correspond to certain features, and each feature may not have same impact on the output, right. Obviously, there are many evidence of these. So, that is why we have a control over the weights. We can vary the weights, we can optimize the weights, that is what we have in our in our domain. So, once we multiply each of these inputs with the weights, we get some kind of a W0 x0, W1 x1 to Wn xn, right. Then we sum it over, okay, because inputs multiplied by each weight factors, sum it over, and this sum is then basically kind of a basically kind of a worked out a activation function, correct. So, this is the activation function here, right, that is called activation function, and this activation function will give an output. These outputs again feed to the next neuron. So, therefore, it is like a multi-level structure, correct. So, this is exactly what we can write it down. You can see x1 w1 x2 w2 all this is sum it over, this is called summation unit. Then we just transfer, we use a transfer function activation function to get an output, right. That is what is how that neural network works. So, I just showed it in a very typical manner. Here you can see that again sum it over applied on a functions, and then we get output like this. This is the output. Well, there are different types of networks obviously exist, but before we go that, I would like to go back to the board and explain you how these things work in a very simple manner, okay, so that you do not forget it for your purpose. So, we have to find mathematical representation of the biological processing, okay, biological neural systems. So, what are these mathematical representation? Remember, we are talking about machine learning, data and data processing. So, we need to talk about mathematical representation of these neural thing. So, basically NN or ANN, okay, is nothing but a series of functional transformation. Series of functional transformation, right. What are these functional transformation? That is what we are going to discuss step by step. Since you have seen the biological neuron and also analogy with respect to the ANN and NN, so we will talk about how this functional transformation happens. So, let us talk about step by step. So, step 1, what is that step? It is nothing but linear combination of input variables. That is as usual I just described with you. Input variables can be xi where I going to 1 to n, or rather better to write a different variable 1 to d. So, what is that? So, I can write down aj as summation of I going to d xi, sorry, I have to write w, right, wji, please look at the symbols, okay, plus let me explain each of this. So, what I write? I wrote aj is equal to, did I write aj? Yeah, aj is equal to I going to 1 to d wij xi plus wi0 wj0, right. I also write superscript 1. So, let me explain why these of these. So, here j will go into 1 to m, right, because we are doing series of functional transformations and these transformations can go up to 1 to m, right, that is why I write. So, I can go to 1 to d because there are d input variables, but j can go to 1 to m because there are m functional transformations, okay, m different types of transformation possible. So, now 1 stands for level or layer 1, that is the first layer, okay. This is the first layer in your neural network, that is why 1 stands for that. What is wj0? This is called bias, okay. What are these biases? These are very simple, that we have, suppose we have data from xi I going to 1 to d. Obviously, data will also have error bars, right. You understand that data will have experimental data or theoretical data will have some error. How to take care of that? So, when you transform, we can add a term like this, which can take care of the variation of data, right. Data will have mean, and from that it will vary it, right. That is what is called mean plus standard deviation. So, Wj0 is a bias which is applied on the first linear combination of the input variable or first transformation. Okay. That is what is called bias, and 0 means what? Here I is 0. That means what? You are adding some kind of a things which does not depends on I, separate. You can see that this summation is about I, this is not. Okay. But this will depend upon j, whichever how many layers you are using. Okay. If you are using m layers, so that means this transformation will for each layer one by one will happen. And Wij or Wji rather are weights. So, in the slides I shown a very simple picture, right, W1, W2, W3, but here I am making a making a mathematical representation of the network, thinking that there are multiple such layer exist. Okay. So, let me just draw it here for the sake of your understanding with a different color of maybe pen. So, let us say I have inputs, okay. These are inputs. So, these are fed, right. You can always have all this transformation possible. Am I clear? You can have this this combinations of the inputs weights everything. So, you do the transformation, then it comes out of the transformation, that is called layer 1. Okay, let me write layer 1. Now, again these are actually inputs to the next layer. So, this is layer 2, and similar thing done. Again these inputs are multiplied by these weights, transformed by activation functions, and output is created. This is the layer 2. You can keep on doing this till you have output. This is the output. Okay. So, you can keep on doing that. So, this is layer 3, layer 2, layer 1. Let me write this way better. So, that is why these J's comes into picture. Each of these are talking about one layer, okay, and this is called multi-layer neural network. Instead, you can have a simple 2 layers, input, one processing layer, and output. That is the simplest possible thing I was talking in my slides. So, I have inputs, then one layer where everything will be done, then you have output. These layers are missing, right. So, most of these layers in between, they are called hidden layer. That is why in the neural network you will see these guys are called hidden, and that is why many people say neural network is just like a black box. Okay. Nobody knows what is happening inside these hidden layers, no one knows. So, that is why we always do not write all this how many layers. You can use hundreds of layers. In many of the deep learning methods, you can use even thousands of layers, such layers, and do the calculation depending on what is your computational power and how much time you can invest on that. Okay, am I clear? So, that is why this J comes into picture. That is the significance of J. I is obviously very easy. I is nothing but input variables, right. How many input data you have? These ones. You have 5 input data, I become 5, 1, 2, 3, 4, 5. If you have hundreds of input data, you become I become 100, right. That is why you put I equal to 1 to D, and J is basically how many layers you are doing that. Okay. So, J changes that way. So, now this step 2, what you do? Step 2, basically each of these edges are transformed using a, so each edges are transformed how they are transformed? Using a different nonlinear activation function. I have already discussed with you that one of these function is a sigmoid function. Remember this different nonlinear, many people call transformation, many people call activation function. So, activation or transformation. Function. Okay. So, edges are transformed by this. Okay. That is what is the next step. So, that means what? I can write down that Jj is nothing but h of h. H is the transformation function. It can be sigmoid, it can be many other function. I will show you just in a couple of minutes after how this transformation function can vary. So, what is the step 3 then? Step 3 is these values are again linearly combined, these jj's are again linearly combined, like in first step inputs are combined, here linearly combined to provide output unit activation. So, let me write down what is that. So, I can write down AK you have to remember this IJK, okay. W Kj layer number 2 Jj plus W K0, okay. Am I clear? So, these are the 3 important steps or mathematical representation of the steps for ANN. First you combine the input variables and this is the way it is combined, then these are transformed using a different activation function, and these activation after transformation these transform values are again linearly combined for the next layer. You can see 2 is given, next layer, okay. And this is done after another one after another. So, in the last step after you do so many times, you can do many times, okay. So, this 2, 3, 4, 5, 6 how many whatever times we can get output from this, okay, and yk is always considered output, okay. That is a step 4. You can stop at any level, that means you can stop even after first, okay. You can stop after second, after third, or even after hundreds of these layers. That is how the whole thing is done. Remember this. This is how the whole aspects are spelled out or done, okay. So, therefore, there are basically several stages of processing, and these stages you have to remember in your when you describe this, okay. So, now let me just go back to I will come back to these slides in the next lecture. Let me just go back and show the activation functions, okay. There are different activation functions are used, right. So, let us say first activation function is basically unit step, that is what phi j can be 0 when j is negative, is 0.5 when j is 0 and 1 which is j is equal to greater than 0. That is what it looks like, you can see 1D curves. It is 0 when z is 0 or less than 0, 1 when it is more than 0. You can also have sine functions, it is shown similar way, -1 to +1. Linear function is very easy. This is called Adaline linear function. So, you can see that, correct. Piecewise linear function, it is not continuous, that is a piecewise. 1 when z is more than half, you can see this is half, right, and it is between is j plus half when it is between half and minus half, and 0 when it is less than minus half. Sigmoid I told you, I do not need to do that. This is how it looks like. It is used in logistic regression quite a lot, or even multi-layer networks widely used. You can use hyperbolic tangent. Another important function which is used is called ReLU or rectifier linear unit. Remember this, ReLU transform to rectifier linear unit is basically maximum of 0 and 1. Basically that means what? It is same as like a linear functions, but the negative side is a value of 0. So, it basically removes all the negative values, consider only positive values, linearly increases, you can see that. And you can have also soft plus, which is nothing but a log of 1 plus exponential z, right. This is also used in multi-net. These curves are very important for you. So, that means what? In many of these neural networks, we can basically use different kinds of activation function to transform the edges. These edges are transformed, you can see here. So, edge is what I discussed just now, edge is what is changing depending on the different kinds of transformation functions. So, edges are made first, then transformed by edge, and then again linearly combined to do that. So, this is how the neural network actually functions, and different types of. Now, I will talk about it in the next part of the lecture, how this can be managed in different ways. Okay. So, let us stop here, we come back to the next part of the lecture soon.